Hey Data Junkies, welcome back again. So glad to see you with me. I'm your host Shawn Janzen. We're continuing our talk on correlations, and in this particular video here we're going to be doing these correlations in R, and we're doing a little bit of work with scatter plots too. It's going to be part 1 on scatter plots. I'm going to give you a second short video on how we're adapting some of the scatter plots with more in the next one. So let's go ahead and just jump right in that we're going to be conducting these correlations in R, moving in. So in this case, let's start with just a short discussion on the different correlation-specific functions that we're going to be using in R. The COR function and the COR.test function. Each one gives us similar things. They both give us the different correlations we're going to be working on. Pearson's R that we've already talked about, Spearman's rho and Kendall's tau, which we're going to be talking about in future videos. Both of these functions give us both types of correlations. Now, core.test is the one we're actually going to use for statistical testing here, and that one's going to give us p-values and confidence intervals, where the regular core function does not. However, the core function gives us access to do multiple correlations at once, a topic that we're going to call correlation matrices in a future, and we're going to talk about those in a future video, where core.test does not. So just keep in mind, depending on what your purpose is and how many correlations you need to test, you're going to need one function or the other. Now let's go ahead and replicate our example from the previous video where we had the comparison of the number of environmentally related ocean hashtags being used on Twitter and the number of other environmental sorts of causes supported online. So in this case I'm creating two separate vectors. They're standalone vectors at the moment. They're not part of a common data set. You could make them part of a common data set as you want, but for this example I'm leaving them separate, and so I'm inputting that data into R, just using a standard columning function. And then I'm also making a third variable that's going to come in handy when we do our plots later, and I'm going to call that one participant, and that just contains the participant numbers. There were 5 of them, so it counts 1 through 5. And keep in mind, when you're putting this data in, the ordering becomes very important. You don't want to mix up, somebody's y variable with their x variables and things like that. So just to kind of help illustrate where we're moving into the confirming the covariance, I'm going to start with variance here. And the variance function is just VAR. And we're doing one variable at a time, so the variance of ocean is 2.8. The variance of causes is 8.5. And remember, this is a measure that talks about the distances from their mean squared overall. So how much spread is there, how much variation is there in the error of each data point from its mean. We can go ahead and change into the covariance mode by using a covariance function, COV. And note the COV function, plays with the data nicely when it tends to be more of in a data frame rather than standalone vectors. So in this case, what I've gone ahead and done is I've nested ocean and causes inside of a data frame, so it becomes a data frame just for the purposes of this function, and then going into the covariance function there. If you already have data points inside of a data set, you don't need to worry about wrapping it inside a data.frame function. All you have to do is specify dataset $variable1, comma, dataset $variable2, and you're good to go. Now in the covariance output here, we get into a matrix form. Both of our variables appear in the rows and the columns, and on the diagonal, where we have the same variables meeting, we get their variances. On the last slide, we just showed that the variance of ocean was 2.8, and in the covariance function, we see ocean and ocean gives us the variance of 2.8. Same thing for causes at 8.5. But what we then get where oceans meet causes on both the lower and upper halves of the matrix, we have 4.25, which was the covariance we calculated in the previous video when we did this by hand. Now, with most of these matrices here, keep in mind that that's going to be a mirrored effect between the lower left and the upper right. So you really only need to look at one half. It's going to be the same values on the other half of the matrix. And right now we only have a 2 by 2, but if we were to have larger and more variables in place, we'll see those later, you're going to see that you're going to get a single covariance for each intersection of a pair of variables. Now we can go from COV to do the covariance to COR to get the correlation. And correlation doesn't care if it's in a sort of a data frame setup or not, so I'm just doing COR on ocean comma causes. Doesn't matter which one comes first or second, and it gives me the correlation 0.87 rounded, and that matches up with what we had in the previous video. Yay us! So let's go ahead and see what this looks like when we plot it out a little bit. Now, when we go ahead and plot this, I've got 2 of them out. They're the same data points being plotted, and I've got the code for you below the plots themselves. just as a brief reminder, all of the code generated for the examples and the plots here are provided for you in the R scripts that accompany these video lecture series. Now in the one on the left, we just did sort of a baseline plot. I have some extra options in there with the CEX and whatnot. Those are just to adjust some of the font sizings on things, so when I put these into the slides, it's a little more visually accessible for you. And we see that on the x-axis, it starts at 4 and goes to 8, and on the y-axis, it starts at 8 and goes upwards of 15. And so in this case here, we see our plot points out and the relationships between them, but what I wanted to show you mostly is that this isn't to a real scale. Both of these variables here are ratios, they have true zeros, so if we were to rescale both of the axes to 0, we get a better real-world representation of where the data points fit in terms of their cloud and movement around them and things like that. So in the second plot, I've rescaled the axes to start at 0 and go a little bit beyond the maximum data points that they had there. So on X it goes from 0 to 9, on Y it goes from 0 to 19, and we can see how the data points fit. Keep in mind, when we were first learning how to do plots in R, we had a discussion about choosing if we want to portray things close to the data points or more true to scale when they starts at 0. And that just, it makes a difference when you're telling your data story and the messages that you're going to convey. And you want to make sure you convey the right message for your audience. Now let's go ahead and talk about putting these into another example here. I have to give a shout out to Andy Field. He's got an amazing book on statistics using R. It's a big, heavy book. But it's a fantastic book, one that I highly recommend you add to your collection, especially if you're going to be revisiting statistics repeatedly, or if you're going to take a longer course and whatnot. It's a good one to have. So in this case, I'm using the data he had from his example there, but I'm taking it a step farther in how it's being used and tested and things like that. So I just wanted to give him the shout out for the data cred. Now, in this case, his data points were on test anxiety, and it's really talking about differences with anxiety and performance, but there's a couple other variables in there we're going to take into account. The data point has 103 participants. They're all students. The measures in the data are how much time has someone spent revising their work in hours, how much exam performance they had. This is measured in percentage of how well they did on the test, high value being a higher score, and exam anxiety. This is an EAQ. It's a test that they can take that kind of gives you a representative measure of how much anxiety they have leading up at a given time before the exam. And it's out of 100, where 100 means more anxiety. And we have an additional variable that gives us a gender variable as well. That's going to come into play later. So I'm going to bring the data into R. I just want to give a brief note that this is a .dat file, .dat. It's another way of storing text, I'm sorry, not text, but data in different containers. And so in order to bring this into R, we're going to use a function called read.delim. Read.delim, D-E-L-I-M. Add this into your toolkit of different options right along with read.csv, scan, load data, all different ways we can get data into R. And I'm using this to assign it to an object I'm calling exam data with a capital D on data. I'm going to run a structure on this, and this is going to give me a quick shout to show me what variables are inside this data frame. And I can confirm it has 103 observations across the 5 variables I mentioned. It adds a variable called code I didn't mention before. That's just a tracking number to keep a unique identifier for each of the participants. And I can see that when it brought it into R, that all of the variables are either numeric or integer, with the exception of gender, which is factor with levels from male and female. We are right where we need to be. So I'm going to do a quick summary on these just to kind of see the spreads and how the data looks, get a sense of the minimums and maximums and the means. The code column, that's pretty irrelevant because they're just unique values representing the participants. And the gender column on the other side, that's just giving me a count between females and males, but it's good to see that they're relatively balanced. And the spreads on revision go from like 0 to 98, so we've got a wide range of people revising their work with an average of almost 20 hours. Exam, also a wide spread from about 2% to 100%, 100% being a perfect score on their test, with an average of about 56, median at 60, so moderating performance there. And anxiety goes from about 0.05 all the way up to about 0.9758. So a wide range there with a median of 79 and a mean of 74. So again, pretty high anxiety overall. Now let's go ahead and see how we're going to put this into R, and I want to give a I want to give a brief moment to talk about an option that we can do in R. If you're doing your correlation and it gives you an NA, add an option, use equals complete dot obs in quotation marks. That's complete.obs in quotes, single or double quotes. And what this is going to do is it's going to parse out. It's going to do that sort of like if it's missing on one or both of the variables, skip it. Only use observations that have values for both your x and your y. The core function does not work with an na.rm equals true like we would use for a mean or standard deviation, so this is going to take the place of that. There are other types and options we have for the use and other things you can check out in the core function, but I'm going to ask you to check out the help documentation files to learn more about those. So here though on the slide, I'm just going to show you briefly how they work with both of these. The core function, we saw this previously, is just core and then the two variables you want to use. So in this case I'm using exam and anxiety, and I get a correlation value of negative 0.44. Negative 0.44, it's about a moderate negative correlation, so that's saying that as your level of anxiety goes down, your exam score goes up. Or as your exam score goes down, your level of anxiety was going higher. And that's just that sort of relationship between them, and there's a moderate relationship there. In the second version, I have the exact same core function, but I've added the use equals complete.obs so you can see how it's being used, even though I didn't need it. I had a correlation value. And I'm also including method equals Pearson. Pearson's R is the default R correlation that we have so far, and that's the default for this particular function. But the method option will allow us to change it later, and we're going to see it when we get into the nonparametrics, the other versions we can use. When I want to go ahead and do some of my significance testing, then I need to change gears from core to core.test. And I have options in here to specify in my core.test. I have an alt option where I can choose two-sided, greater or less, where two-sided is my non-directional two-tail test, and my greater is my upper tail, my less is my lower tail directional hypothesis testing. It also gives me a confidence level that I can indicate with conf.level. The default is 95%, but you can change it to 99, 98, 90, or whatever other level it is you'd be happy with. So let's go ahead and use an anxiety and exam again to see how this fits out. And so when I do that, it reports a Pearson product moment. It tells me the data points that I'm asking for the correlation on. Remember that the p-values for R are calculated with a t-distribution, so it gives me a t-statistic along with degrees of freedom and the p-value for it. In this case, note our p-value is incredibly small. It's 3.12 e negative 0.06, so it's scientific notation, very small value, and we never report p-values in scientific notation. If it's that small, just report it as p is less than your alpha and be done with it. Now, then it goes ahead and it gives us the alternative hypothesis. We did the two-tail version, non-directional, so it tells us that this is the p-value and t-score associated with the alternative, that the correlation is not 0. It gives us our confidence intervals, and then the same correlation we had before of negative 0.44. Fantastic. Let's go ahead and look at this in terms of a plot. On the right side of the screen, I have a correlation scatter plot, and the data points are in red. There is a blue line going through it that kind of tracks along and shows you just sort of like where the data points are, and as they're moving, the line moves with the data points. And then there's a green dotted line, dashed line, that kind of goes through in a straight line. It bisects through. That one is what we call a best fit line. The best fit line is where it's just like, as I said before, it's going to try and find where, at what angle can it cut through the data to kind of minimize the distances from each of those data points to that line. It's a regression line, and we're going to talk more about those when we get to the regression section, but don't worry about the specifics on that right now. Just understand that that line helps us understand our correlation and the direction of it. So on the left side, I have all of the code used to generate this particular plot, and so what I really want to draw your attention to is that it is just a plot with X and Y specified, and then a bunch of extra options I did to kind of make it more of a presentation quality and fit nicely onto the slide here for you. All of the options are ones that you should have seen before in some of the previous lecture materials, so nothing new here as far as that goes. Now, the next two functions, though, lines and AB line, those are relatively new for you. So the lines function is what we use to add an additional type of line to it. In this case, we're adding a lowest line, and the lowest line is the blue line that just sort of tracks along with the pattern and the shape of the data there, and it's allowed to curve. This one is indicated with blue, and the LWD option just specifies the thickness of the line. How thin or thick is it? Higher the number, the more thick it is. AB line function, inside there I'm specifying an LM, which stands for linear model. This is actually a regression function here, but again, like I said, we'll talk more about that when we get to the regression section. But it's being indicated as dark green, same thickness of 4. LTY switches it from being a solid line to a dashed line when LTY equals 2. So we add both of those after the plot function, and it will overlay those lines on top of our most recent plot. If you try to run them by themselves without the plot, they're not going to go anywhere. So let's go ahead and do another correlation, and we'll do another scatter plot after that, see how they look. So now we're doing a correlation test between how much time someone spends revising their work and their exam score. Before we saw there was a negative relationship between anxiety and exam. How about revision and exam? So we go ahead and run the core.test on our two variables there. It tells us, again, an extremely tiny p-value on a correlation that rounds to positive 0.4. So it's a moderately sized correlation, and it's statistically significant. So we can say that as the amount of time you spend revising your work goes up, so does your exam score, which kind of makes sense. That, if you do more time studying and revising your work, you're going to learn the material better for your next exam. May that be a hint for you guys in class. So let's go ahead and plot this out. And here in our scatter plot, we can see that a lot of the data points are hugging to the left side, showing that the majority of students spend somewhere probably between 0 to 30 hours revising their work over the course of the term before their final exam. And we fit a lowest line and a best fit line directly through there, and it looks like it's tracking out fairly well. But again, the correlation was only 0.4. It's moderate, so we still have a large cloud of data around that best fit line. It's got a long way to go before it becomes a strong correlation and tightens up around the data points there. And again, no new real code here as far as the R side of things go. A lot of it's the same materials you've seen before. So now we're doing a third correlation example between anxiety and revision. We're taking exam scores out of the line here, and we're just seeing how much time you spend revising, does that affect how much anxiety you're having? So we're doing a core.test on anxiety and revise. It doesn't matter which variable goes first or second. And then it's going to produce, again, an extremely tiny p-value, so we're going to be statistically significant at most levels of alpha. And it shows that I have a correlation value that rounds to negative 0.7. Negative 0.7. That's a negative strong correlation. So that's saying that the more time you spend revising, the less anxiety you have. Or the more anxiety you have, the less time you probably spent revising. And it's statistically significant, which again kind of makes sense for most people who study. Now, if I plot this out, we're going to see that most of the data points are clustering down in the lower right. So most people are having higher levels of anxiety, and they've studied in fewer hours compared to those who studied more. The more people were studying, the less anxiety they tended to have. And we don't have a ton of data points out there away from the cloud, so we have to be careful about making too many inferences in that regard. But that is what the data supports. And it just might happen to be that there aren't a lot of people that are spending massive amounts of time revising their work. So we'll take those things into context when we do our interpretations. Again, the code here is exactly the same as in previous plot slides. The only thing that changes is the names of the variables inside of the plot and the two line functions there. So let's go ahead and talk about how we can report this up in APA. In this case, I'm going to say that exam performance was significantly correlated with exam anxiety with an R of negative 0.44 and time spent revising your work at positive 0.4. The time spent revising was also correlated with exam anxiety. R is equal to negative 0.7, and all of the p-values were less than an alpha of 0.001, which is extremely small. I could have put the p-value up against and next to each individual R, but it seemed a little redundant since all of them were so small and I was using the same level of alpha, so it was okay with putting that at the very end, saying, here's all the correlations, and they share a common alpha and a common p being less than alpha. And with that, this is all you really need to go ahead and do the correlations in R, to run the statistical significance testing to see if there are statistical relations with them or not, and get ourselves started with making scatter plots with best fit lines. You don't have to worry about the lowest line when you're doing your plots. That's just something I kind of wanted to show you, but certainly be able to do a scatter plot with a best fit line, the AB line function, and be able to generate your results in an APA format. I'll then take us to the next video where I'm going to spruce up our scatter plots a little bit with a third variable. And with that, I'll see you all next time.